Alright, stats class, how we doing? I'm going to do our best here to try and get through these notes on a recording, and hopefully this works out well for you guys. This week's focus is section 8.1 about this thing called hypothesis testing. And that's the first question, hypothesis testing. What is it? And it is this, it is a decision-making process for evaluating choices evaluating claims, I should say. That's probably a better word than choices, about a population. Okay, so this can come in all kinds of shapes and sizes. You could be making a claim about the effect a medicine has on a body, about the number of cars going through an intersection, about how much money you spend on something, whatever. And this is something that statisticians will use all the time. There's two parts that come to this hypothesis testing. The first is this thing called the null hypothesis. The second one's the alternative hypothesis. And this is kind of like the foundation for what we're doing here. The null hypothesis is, think of it as your starting point, okay? It's generally going to be whatever your mean is, and it's denoted by this H0. Sometimes you hear that called H0. H0 represents the null hypothesis. The alternative hypothesis is, if the null is our starting point, then the alternative can be thought of as the change or the difference. And that is represented by H1. Okay, it's a little subscript there. H sub 1 and then H sub 0. So H0 is for the null, H1 is for the alternative. Okay, so part of what we're doing here is trying to identify these things first. Some examples that will help us with that are here. A medical researcher is interested in finding out whether a new medication will have any side effects on the patient's pulse rate. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? The pulse rate for the population under study is 82 beats per minute. So all we're doing right now is identifying the null hypothesis. Remember, it's H0, H sub 0. That is going to be 82. Okay, it's given to us that the population mean was 82 beats per minute. So that's our starting point, right? That's where we're starting. That's our null hypothesis. The alternative then, it's going to take a format of this. It's going to be the mean not equal to 82. Okay? Remember, I said the alternative hypothesis is thought of as like the change, the difference. You know, what's different about the starting point. For this particular study, we are trying to figure out, okay, is your heart rate greater or less than, as long as it's not equal to 82. That's kind of what we're thinking about. Okay. This, when you have the alternative hypothesis not equal to the mean, that is an example of a two-tailed test. Okay, and you can think of that as like above and below. I say that meaning like we can be above 82 or below 82, right? Doesn't really matter here if it's down to 80 or 78, or if it goes up to like 85 or 90 or 92. Above or below are things that could happen in this scenario. Okay, so that's a two-tailed test. We'll come back to some of this here later too. The next one, a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of these batteries is 36 months. So let's start with our null hypothesis, H0, H sub 0. Our mean here, mu, is equal to 36. And this time our alternative hypothesis, mu, this is going to be just on one end now. We only want to increase, so we are only looking at things greater than 36. Okay, and this is an example of a right-tailed test. We call it right-tailed because we are only above the mean. You know, you think about like your normal distributions, right? And if you are above something, you're going to be to the right of that. Okay? Whereas like in the first one, I guess I could have sketched this out before. If you could be above or below, you know, when we were not equals to. So that's why it was two-tailed. The last one here, or the next example, a contractor wishes to lower heating bills by using a special type of insulation. The average monthly heating bill is $78. So our null hypothesis, H0, mu equals 78. Again, that's our starting point. That's where we're beginning this whole thing. The alternative hypothesis, this time mu, we want it to be less than 78. That's what we're looking for, okay? This would be an example of a left-tailed test, or think of it as below, okay? Because again, if you got your curve, that's a horrible curve. We're looking now at situations where we are less than the mean. We are below, okay? We're going to be in that range down there, okay? Some more practice here. Finding the null and alternative hypothesis, okay? I really want to get this down because I know this is new. It might not make a ton of sense yet, so I'm really trying to just throw a bunch of examples at you, and hopefully it starts to sink in. Let's look at letter A. A researcher thinks that if expectant mothers use vitamin pills, the birth weight of the babies will increase. The average birth weight is 8.6 pounds. So our null hypothesis, H naught, mu equals 8.6. Now let's identify the alternative hypothesis. Okay, is it going to be less than, or greater than, or either? And in this particular case, it doesn't really specify if it's less than. We are only looking at if the birth weight will increase. Okay, so we want mu greater than 8.6. I started writing something there, kind of messy. That's all right. Greater than 8.6, okay, because we're looking for an increase. Letter B, an engineer wants to decrease the number of defects in compact disc production. The mean number of defects per 1,000 disc is 18. So that means H naught mu equals 18. And then our alternative hypothesis, H1, keyword from above was that engineer wants to decrease the number. Okay, we are now less than 18 for the alternative hypothesis. And letter C, a psychologist studies the impact of listening to soft music during a test. The psychologist is unsure whether the grades will be higher or lower. The mean test score was 73. So our starting point, that mean test score, was mu equals 73. For our alternative hypothesis, this is one where mu, it could be above, it could be below, so we're just going to say that it's not equal to 73. Okay. Now, once we've established what the hypothesis is, kind of where we're starting, the researcher, in any of these cases, must perform some kind of statistical test. Okay, that's kind of the next phase of this whole thing. Now, I say that, some kind of statistical test to make decisions about the hypothesis. Now, I say that, and we're not really going to be doing these tests ourselves. Okay, we are going to be given the information from these tests, and we are evaluating whether these are good or bad claims. Okay, and we'll talk more about that here in a second. But this start point here kind of reiterates that these tests are designed to help us figure out if we want to reject the null hypothesis. It's a big part of what we're trying to do here. We're trying to look at the null hypothesis, our starting point, and figure out, man, was this a good place to start? Was this accurate? Or is this probably not a very good, guess for our data here? We'll typically be comparing samples. Samples meaning, like, you can think of it like X bar, things that we've gotten in smaller groups to the hypothesis. So that was, again, what we started with. That was our mu. That's our H naught. To help us make a decision. Okay, go ahead and go to the next page, or flip it over, I guess. It's just one page. Evidence for these comes from comparing the mean from a sample. So we just kind of said that on the previous side. And the hypothesized mean. Okay. The larger the disparity between these two, like the mean and your hypothesis, the more likely we are to reject this null hypothesis. Whereas the smaller the disparity, the more likely we are to not reject the null hypothesis. Let me show you an example of what I'm talking about here. This isn't on your notes, so just try and jot it in the margins or above or something. But on the previous page, we talked about one study where we were talking about heartbeats per minute. And we said our our null hypothesis was the mean was 82. That's where we were starting. Okay. Now let's say the study happens and you get some test results back and your sample mean was 90. Okay. Well, in a situation like this where your sample mean is a pretty good amount above your null hypothesis, this is probably a situation where you would reject the null hypothesis. But let's say you had your sample mean was, I don't know, 83. Something that's like pretty dang close, okay? Well, your conclusion there might be to not reject, okay? Because that doesn't necessarily mean that the initial hypothesis was wrong, right? Because 82 is where we started. If you got 83 for your sample mean, it doesn't mean that 82 is necessarily wrong. There could have been just, a little bit of a goofy sample size or whatever. So that's a situation where we wouldn't reject. And I emphasize that because when we're doing this, we aren't saying that something is necessarily true. Okay, I underline that because that is important to understand here. We're not saying that the null hypothesis is absolutely true. What we are doing is we are either rejecting it or we are not rejecting it. Okay. An example I put up here that I think hopefully kind of makes sense with all this in mind is think of a jury trial. Okay, your null hypothesis here, H naught, would be that the defendant is innocent. And then H1, your alternative hypothesis, would be the defendant is guilty. Okay, the defendant of this trial will either be convicted or acquitted, right? Okay, so those are the only two outcomes of any trial. Either convicted or you're acquitted. This sets us up for 4 possible outcomes here in this little box. So across the top, your defendant is either innocent or he's guilty. He's only one of 2 things. Like in reality, he's either one of these 2, right? There's no other middle ground. And then in the jury's either going to convict him or they will acquit him, meaning he is not charged. So these are your 4 outcomes here, right? Either the person is innocent and they are convicted, or they are innocent and they are acquitted, or they are guilty and they are convicted, or they are guilty and they are acquitted. Now, 2 of these scenarios are the correct course of action, right? If you are innocent and you are acquitted, that is a correct action, okay? The jury acquits you and you're innocent, that's what we want. If you are guilty and they convict you, that is also correct. So those are the 2 correct outcomes for this whole thing. Now, that means there are 2 incorrect outcomes, okay? The first one is if you are innocent and they convict you, we call that a type 1 error. The other one, if you are guilty and they acquit you, that is a type 2 error. Now this was just an example, but this follows the same thing we do with our null hypothesis being true or our null hypothesis being not true. And then it's the same idea. Are we going to reject the null hypothesis or are we going to not reject it? Okay. So when you're evaluating this null hypothesis, if your null hypothesis is true and you reject it, that is a type 1 error. You don't want to reject something that's true, right? If it's true, you want to not reject it. That would make this box correct. Now, if your null hypothesis was not true and you rejected it, that would be the correct course of action. And if your null hypothesis was not true and you did not reject it, that would be a type 2 error.